Welcome back to The Explainer. Today, we're diving into a material that you might not know by name, but I guarantee it is fundamentally shaping the future of modern engineering, behind the scenes. We're talking about PDMS, or if you want to use its full chemical name, polydimethylsiloxane. It's this incredibly versatile, transparent, rubbery silicone elastomer that has basically revolutionized everything from how we study human blood flow all the way to how we cool our most advanced supercomputers. I am so excited to unpack this with you today.
So here's our roadmap for today's explainer. We'll start with the rise of PDMS, then we'll weigh its pros and cons. After that, we'll get into biomicrofluidics, look at some really cool heat transfer innovations, and finally, wrap up with how it's being used for sustainable face masks.
All right, let's jump right into Section 1, the rise of PDMS. To really appreciate this stuff, we have to look back a bit. In the early 70s, engineers basically had to rely on rigid glass microchannels to study things like blood flow. But fast forward to the early 2000s, and the introduction of PDMS soft lithography opened up entirely new doors for microfluidics. And honestly, the fabrication process itself is a massive part of why it's so popular. It's beautifully simple. You just mix a base polymer with a curing agent, pour that liquid PDMS directly onto a mold, degas it in a vacuum to pull out all those trapped air bubbles, bake it in an oven at around 60 to 80 degrees Celsius, and then literally just peel it off the mold. Just like that, you've got a highly complex device ready to go.
Now, to put why this shift from glass was such a game changer into perspective, we really have to talk about flexibility. If you look at the Young's modulus scale, traditional glass sits at a highly rigid 50 gigapascals. It doesn't give. But PDMS? It sits way down at just 1 to 3 megapascals. It is incredibly soft, elastic, and flexible. And that flexibility is absolutely crucial because modern engineering applications demand device walls that can dynamically stretch and bounce back to their original shape. You know, kind of like actual human blood vessels.
Because it's so flexible and easy to mold, PDMS has spawned this massive web of applications. We're seeing it pop up across totally distinct engineering fields. Engineers are using it to create blood analogs, micropumps, complex organ-on-a-chip platforms for biology, and even totally different macro-scale things like sustainable consumer face masks. It's the perfect bridge between biological simulation and hardcore mechanical engineering.
Which brings us to Section 2. Weighing the pros and cons. Now, no material is completely perfect, right? When we stack PDMS up against the traditional heavyweights, the engineering trade-offs become pretty clear. Glass is fantastic because it's inert and transparent, but it's super fragile and extremely expensive to shape. Silicon is brilliant for thermal stability at the nanoscale, but it's totally opaque, costs a fortune, and usually requires a dedicated cleanroom to work with. PDMS really hits a sweet spot. It gives us that vital optical transparency for real-time observation, it's biocompatible, and it's gas-permeable, meaning cells inside it can actually breathe, all through that low-cost fabrication we just talked about. But it definitely has one notable weakness, its hydrophobic nature.
So, what does hydrophobicity actually mean in this context? It means the natural surface of PDMS repels water. Think of how water just beads right up on a freshly waxed car. If you're trying to flow biological fluids through tiny channels, that's a huge headache. Plus, a hydrophobic surface can actively absorb certain liquid dyes and proteins right into the channel walls, which completely skews your test results. But engineers are clever. To get around this, they blast the PDMS with surface treatments like oxygen plasma or UV irradiation. This actually flips the surface to become hydrophilic, meaning it suddenly loves and attracts water, which allows for smooth liquid flow and lets cells adhere perfectly without ruining the device itself.
Let's move on to Section 3, biomicrofluidics and biomodels.
Because PDMS is so transparent, breathable, and friendly to living cells, it acts as the absolute perfect artificial environment to replicate human tissue. Engineers use it to create what we call in vitro biomodels, or phantoms, which physically mimic the flexible, thin walls of human arteries. This means medical researchers can safely replicate a complex cardiovascular disease, watch how blood flows through a dangerous aneurysm, or even observe the behavior of cancer cells under stress. It's also the driving force behind organ-on-a-chip platforms, these tiny bioengineered devices that replicate how entire human organs function so we can test drug reactions in real time. And thanks to that crystal-clear transparency, researchers can point high-speed microscopes right at the action to gather immediate hard data.
And here's why this matters immensely in the real world. Today, medical device design relies heavily on computer algorithms and numerical simulations to predict how fluid will flow. But you can't just blindly trust a computer model when human lives are at stake, right? These physical PDMS biomodels allow engineers to experimentally validate those complex simulations in the real world. By proving that the actual physical fluid behaves exactly as the computer predicted it would, engineers save a massive amount of time and funding because they don't have to produce endless rounds of expensive physical prototypes.
Okay, shifting gears to Section 4, Innovations in Heat Transfer.
Let's step out of the biology lab and look at electronics. Heat dissipation is a massive bottleneck in modern tech. To solve this, engineers have designed completely novel, serpentine-shaped PDMS heat exchangers. Because the material is so flexible, these cooling channels can beautifully contour right over the bumps and grooves of microelectronics, maximizing the physical contact area to pull heat away. We're seeing this deployed in everything from supercomputers to photovoltaic solar panels. And scientists are taking it a step further by mixing alumina nanoparticles directly into the liquid PDMS before it cures. They can drastically boost its thermal conductivity. As a bonus, PDMS naturally resists nanoparticle buildup on its surface, which means the thermal sensors inside these systems stay much cleaner and give way more accurate readings than older traditional setups.
And the results are pretty wild. In direct head-to-head tests, these flexible PDMS heat exchangers actually reduced surface temperatures by an impressive 17% compared to traditional rigid copper-based cooling systems. Honestly, a 17% drop using a low-cost, flexible polymer is a massive leap forward in thermal management. Finally, let's look at Section 5, Sustainable Face Masks.
This is a brilliant macro-scale application. During the pandemic, the world obviously generated mountains of medical waste. To tackle this, engineers figured out a highly sustainable life cycle for PDMS. When a device reaches the end of its life, they grind that used PDMS down into tiny 1mm specks. They take those recycled particles, mix them directly into fresh liquid PDMS at a 5:1 ratio, pour that eco-friendly mix into a mold, and cure it in an oven at 80 degrees for about 40 minutes. The resulting transparent film is then sewn directly onto fabric to create a brand new protective face mask.
As you can see, this entirely closes the loop, turning recycled medical waste right back into a highly functional consumer product. And that clear window in the center is a crucial design element. It solved a major social issue during the height of the pandemic, allowing people to actually see facial expressions and read lips again, which was a huge barrier to communication at the time.
But the real kicker here, the big takeaway, is that integrating that recycled material didn't ruin the performance at all. Rigorous testing proved the mask still maintained about 90% bacterial filtration efficiency, easily qualifying it as a level 2 mask for public spaces. Plus, even with those ground-up recycled particles mixed in, it kept 90% of its optical transparency. And, crucially for the person wearing it, the breathability stayed excellent, falling well below the maximum resistance thresholds. It's just a fantastic example of a certified, highly sustainable engineering solution.
So, as we wrap up this explainer, we're looking at a future that desperately needs both advanced biotechnology and eco-friendly consumer goods. PDMS is sitting right at the intersection of those demands. Think about it. If a single, flexible polymer can safely replicate the complex flow of human blood, efficiently cool down our next-gen supercomputers, and then be ground down and recycled into sustainable gear that lets us smile at each other again, you really have to wonder, what major engineering crisis is PDMS going to solve next? Thank you so much for joining me today to explore the unseen materials shaping our world. Stay curious, and I'll see you in the next explainer.